Now let us talk about the beam. Here we have an accelerator which was constructed in 1980, so it is a rather old accelerator. And the plan was to adapt it so that it could obtain calcium-48. Unfortunately, it was completely unsuitable for this task, because this accelerator had a plasma ion source inside, which was constructed by Markov, Morozov, and Iov under the guidance of Academician Artsimovich. It was a source that was created in the Soviet Union to separate uranium-235 and 238. It was supposed to provide a current of 1 ampere of uranium, so that 50 kilograms of uranium-235, the critical mass for bombs, could thus be gained. However, a current of 1 ampere was not obtained through this source, but rather around 100 or 150 milliampere. But as soon as we started using this source for calcium-48, we were absolutely horrified at the high rate of calcium consumption. After 2 months of hard work, we realized that everything had to be changed. It was necessary to change the entire construction, starting with the use of a different source and positioning the source outside the accelerator, resulting in a source that must work on a completely different principle. It was necessary to receive the beam, inject it from above into the accelerator, before accelerating and extracting it. There was no other way. So a source was chosen, the so-called ECR source. ECR is an abbreviation for electron-cyclotron resonance. Allow me to explain how it works. There is a coil that creates a magnetic field which causes the electrons in the plasma to spin inside this magnetic field. There is also a special loop, not shown here, which creates a high frequency, and the same principle is implemented as in the cyclotron. The electric field spurs on the movement of electrons in a circle so that they receive more energy and begin to ionize neutral atoms more efficiently as they are injected. At first, it runs on helium and the so-called dusty discharge. This is how the ECR works. And then we need to inject calcium into this plasma. It is necessary to inject the calcium so as to minimize the losses. Usually, calcium has a very high rate of oxidation. It is not a metal, it is always in the form of oxide or in the form of chalk, and therefore it is completely useless to heat it, since it is highly refractory. In order to obtain metallic calcium, it is necessary to remove oxygen from it. Therefore, it is necessary to remove oxygen from it in a vacuum, that is, to take some other element that is even more strongly associated with oxygen than calcium. For example, aluminum, and then we would have a calcium atom and alum, which is highly refractory. After that, it is possible to work with calcium as with metal. This should be done according to the chemical technology at temperatures above 450 degrees Celsius. I would like to show you this diagram. This is the pressure of saturated calcium vapor. Here is the point where the calcium metal melts. Here is the point where the calcium metal boils. Here we take calcium oxide and aluminum at room temperature and mix them in a crucible. Then we start heating the crucible, and at about 500 degrees Celsius, metallic calcium is obtained. Then it melts, calcium and aluminum oxide are obtained, and already at this point, at up to 1000 degrees Celsius, We have optimal conditions for the forming of calcium vapors. We can regulate the vapor pressure of calcium simply by controlling the heat. The hotter it is, the more vapor appears. This is a very convenient system, and it was used to inject the calcium vapor. Here, another difficulty arose. We obtained a beam of calcium, but the intensity was 10 times lower than if we used argon gas, because an atom moves until it reaches a surface, sits on the surface and stays there. That is, only those atoms which move through the plasma are active. And then we would like each atom passing through the plasma to begin ionizing, and then it will be captured. However, this probability is small, at only 0.1%. The source was ordered from France. When the French made the source for us, they charged a lot of money for it. The source was brought here, and it turned out that its intensity was lower than when argon was used. In France, the source produced the same result. Then we realized what the problem was and countered it by placing a hot screen heated to a temperature of 1000 degrees Celsius. When the calcium came into contact with the screen, it flew off again. That is, we made metallic calcium which acted like a gas. It's not exactly a gas, of course, but it did not stay on the surface for long, but rather flew from surface to surface and thus crossed the plasma many times. Therefore, the intensity immediately increased tenfold. There was a big scandal in France surrounding the fact that the source had been sold to Russia and that it subsequently provided an intensity 10 times higher than it had in France. I invited the French to come and see how it's done and told them to leave the pioneers behind this design alone. Now everyone uses this design. Here is the diagram. This was the second step, which was very important because only through this process were we able to reach a consumption rate of 0.5 to 1 milligram per hour, which allowed us to work more calmly, despite knowing that the cost of operating the accelerator had increased slightly due to the fact that we were using calcium-48. In order to adapt the source and the spectrum of charges that it provides the accelerator with, took some work. But in the end, a solution was found. At this stage, we do not consider our solution to be optimal, but can only be improved by making changes to the accelerator. In the future, when reproduced in a factory environment, it might be better. Here is a 5+ that worked for us, but this source could have given even more if there had been a 10+ charge. But 10+ did not fit into the characteristics of our accelerator. Here is a graph. There is the ECR source, approximately 1.5 times 10 to the power of 15 calcium neutrals are injected here from this crucible. All charges are drawn from the source. Then a +5 charge is split and taken here, which is about 6%. It passes vertically through the entire magnet, goes to the center, is reflected in the center, then accelerates and exits. And at the output, we have approximately 10 to the power of 13 ions per second in a good instance. That is, the entire procedure has an efficiency of approximately 1%. It was good then, now it will be even better. By itself, this is also a good device, which gives 1%, accelerates the substance to the speed of 0.1% of the speed of light. This is the installation process, and as soon as it was done, the experiments began with calcium-48. Around 3,800 hours were spent at a current intensity of 5 times 10 to the power of 12 in order to irradiate plutonium and curium with calcium-48. And only then did we see the result. Here is an example of how such a source and accelerator work. Here is its intensity. This is 1 microampere of particles, and this is over a period of 50 days. During these 50 days, the characteristics of the accelerator do not vary by more than 0.3%, which is about 1 megaelectron volt. This is permissible. This is the part that was necessary before we had the opportunity to carry out the reaction and observe the formation of nuclei, which then had to be separated.